What are you doing?
What?
Why are you on your iPad all the time? You're supposed to make a no video.
Well, I found this new skill page on kalimath.org. Look, they have all of these nice articles on the foundation of probability theory. And I've just been reading through them for the
Richard,
past
wait.
hours.
We
It's
are
so nice.
Kalimath. Richard, we are Kalimath, and you're supposed to make this video now.
Ooh, sorry, I totally forgot about that. Hey guys, today I'm going to cover the basics of probability theory. The idea behind this video is that in our solutions we would like to use the probabilistic method from time to time. But in order to use it appropriately, you should know about the basic definitions and results from the field. First of all, to define a probability experiment, we need some sort of randomness. And formally, how we introduce this is via a probability space, which consists of the following three ingredients. We start with a set capital omega that we interpret as the set of possible outcomes of our experiment. Note that we are not only interested in probabilities of single outcomes, but rather collections of outcomes, which we call events. So our probability space also consists of a capital A, which is a set of events. As I said, we want to consider collections of outcomes as our events, and therefore one reasonable choice for A would be the set of all subsets of omega. In other words, the power set of omega that we denote by 2 to the omega. However, we want a bit more flexibility in general, and therefore we just force A to be a subset of the power set of omega for now. To get a bit more of a visual understanding for this, let's make an example, namely 2 coin flips. In this case, we care about the order of the flips, so omega contains the sequences of length 2 that are possible coin flip outcomes, namely heads, heads, heads and then tails, or tails and then heads, or tails and tails. And let's just take all subsets of omega as possible events, so A equals to the power set of omega. This is a nice example so far, but we have no probability yet. To solve this, we will define a function on A that maps each event to its probability. We want to be able to do some algebra with that function, which is where the power of probability theory really comes from. But in order to do this, we need A to have some structure. In other words, we will now make some reasonable assumptions that we enforce our set of events to satisfy. Namely, the set omega itself should be contained in A, and this event will have probability 1. Moreover, for any event A in A, we would like the complement, A complement, which we define as omega minus A, to also be an event. We also want to be able to combine events, which means that for A1, A2, and so on, elements of A, we want that their union, namely the union of I going from 1 to infinity of AI, is also an element of A. We call a subset of 2 to the omega with these properties a sigma algebra, where the sigma in this context stands for infinity, referring to the fact that we require countable unions of elements of A to again lie in A. On this structure-rich set A, we can now define a probability distribution P, which is a function mapping all elements of A to a number between 0 and 1. I motivated these requirements on A by the fact that we want P to satisfy some algebraic properties. As we interpret P of an event A as its probability, we have that the probability of our entire set of outcomes, P of omega, should be equal to 1. Secondly, we want to define the probability for a union of events. This time, we only define it for pairwise disjoint A1, A2, and so on elements of A. It makes sense that we define the probability of their union as the sum of I going from 1 to infinity of the probability of AI. If P satisfies these two properties, then we call it a probability distribution on omega A. Now we have finally defined a probability space, namely in this case, the triple omega P is called probability space. There are many possible probability distributions on omega A in this example. However, we make the assumption that our coins are both fair, and right now we want to formalize this in the way that for all outcomes omega in omega, the probability of omega, which is short notation for P of the set containing omega, is always equally likely a quarter. This already defines P uniquely, namely we get that for all events A, P of A equals the size of A divided by 4. This probability distribution P is also called the uniform distribution on omega. We will spend the rest of the chapter with deriving the important algebraic properties of a probability distribution. First of all, the empty set equals omega complement and is therefore an element of A. The probability of the empty set should be 0, which is indeed the case, because by sigma additivity we can get that P of the empty set, which is just the union of countably infinite many empty sets, equals the sum of I equals 1 to infinity of P of the empty set, which we can rearrange to P of empty set equals 0. From this, we also get a finite additivity for P, namely if A and B are disjoint elements of A, then P of A union B is equal to P of A plus P of B plus P of empty set plus P of empty set and so on. Since all of these summands equal 0, this is 0, and indeed P of A union B equals P of A plus P of B. We can also write this in a slightly different way, namely for events A and B such that A is a subset of B, we have P of B equals P of A plus P of B minus A. Since P of B minus A is non-negative, this is greater than or equal to P of A. And in total, this statement also is quite intuitive. P of B is greater than or equal to the probability of A, as most of the things we are doing right now should be. As a final remark, we could always set B equals omega here to obtain that P of omega equals P of A plus P of A complement, which we can rearrange to P of A complement equals 1 minus P of A. In the second constraint for P, the sigma additivity, we require the AI to be pairwise disjoint. We are now going to learn about two ways to fix this constraint. The first is the union bound, which gives an upper bound for the probability of the union of arbitrary events. Namely, let's pick A1, A2, and so on from our set A. We can use sigma additivity if we modify these events in such a way that they become pairwise disjoint. We do this by defining Bi to be the set Ai minus the union of j less than I, Aj. Since the union of Bi is equal to the union of Ai, we get the probability of union Ai equals that of union Bi. And now this is just the sum of probabilities of the Bi since they are pairwise disjoint. Note that Bi is a subset of Ai, and therefore by this inequality, each of those summands is less than or equal to P of Ai, which is just the result we wanted to prove. We can also determine the exact value of the probability of the union of Ai using the principle of inclusion-exclusion. This result is also well known in a non-probabilistic formulation. I will give a nice one-line proof for that result, but since it requires expectation, I will have to put it later in the video. We are now ready to define random variables, which will then set us up to go on with expectations. Generally, you can think of a random variable as a function x mapping omega to a set S. Since it really doesn't hurt us and is important for defining the expectation of x, we are going to only care about S, a subset of the real numbers. Moreover, if we want to define the expectation of x, we will need to sum over its possible values. If S is countably infinite, for example, just the set of natural numbers, this is an easy task. However, if S were uncountable, for example, the set of real numbers, this would be more difficult and we would need to replace our summation by an integration. Since this case is not really interesting for us right now, we are going to force S to be countable, in which case x is a discrete random variable. However, this is not quite enough for x being a random variable. For example, we want to be able to evaluate the probability that x is equal to some number x in S. This notation is shorthand in two ways. Namely, this is a shorthand for the probability of the event that capital X equals x, and moreover, we define the event capital X equals x as the set of all omega in omega such that x of omega equals x. Therefore, this probability is only defined if this is indeed an event in A. So we add to our definition of a random variable that for all little x in S, we have the set capital X equals to x is an element of A. And in this case, we call x a random variable, or short, just RV. Let's continue our example here. Since A was just the power set of omega and omega a finite set, any function from omega to the real numbers will be a discrete random variable. For example, let us just consider x from omega to the set 0, 1, 2, such that x of omega is defined as the number of heads in omega. In this example, x of hh equals 2. We are now going to quickly cover the transformation of random variables. Namely, given any random variable x and a function g from S to t, the composition of g and x is again a random variable that we will denote by g of x. To prove that g of x is indeed a random variable, we need to make sure that this condition still holds. So let us take an element y of t and consider the set g of x equals y. Here, this set again refers to the set of all omega and omega, such that g of x of omega equals y. Omega is in this set if and only if x of omega is mapped to y under g, or in other words, this is equal to the set of x in g inverse of y. But the right side is just the union of x in g inverse of y of x equals x. Since S is countable, this is a countable union. And moreover, the fact that x is a random variable implies that this is contained in A. And now we conclude that since A is a sigma algebra, that all of this is also an element of A. Note that we used S countable here, which hints at the fact that arbitrary random variables need a little bit of a different definition, but we only care about discrete random variables. However, we also see that if t is a subset of the real numbers, g of x will be real valued regardless of the choice of s. Therefore, we don't want to entirely throw away the possibility that s might not be a subset of the real numbers, in which case this random variable would not be real valued, but unless stated otherwise, we also only care about real valued discrete random variables. Indicator random variables can be viewed as the fundamental building blocks of random variables. Namely, for an event A and A, we define the indicator random variable of A, 1A, by 1a of omega equals 1 if omega in A and 0 otherwise. Since A is an event, this function is indeed a random variable. In the next chapter, we will define the expectation of a real-valued random variable. For indicator random variables, this is easy, or at least we can see what value the expectation E of 1a should have intuitively. Namely, this is just the probability of event A occurring. Let's now build a reasonable definition of expectation that satisfies this property. The expectation of a real-valued random variable is again a real number that we interpret as its expected value. Therefore, we want E of 1a equals P of A, but this is not enough to define the expectation uniquely. Note that given a random variable x and a scalar a, we expect the random variable taking the value of x multiplied with a to have the value a times expectation of x. In the same way, for x and y random variables, the random variable returning the value of x plus the value of y should have expectation equal to the sum of expectations of x and y. To sum this up, we want the expectation to be linear, where we define the random variable ax plus by to be the random variable that takes the value a times x of omega plus b times y of omega at a point omega. Since we are working with discrete random variables, this indeed defines the expectation. Namely, we can write a discrete random variable x as the sum of x and s of x times 1 x equals x. Taking the expectation on both sides and applying 1 and 2 yields E of x is equal to the sum of x and s of x times the probability of x equals x. Let's take this as our definition for the expectation of x. We have to be careful though that this sum is indeed defined. Namely, we could have infinitely many summands, not all of which need to be non-negative. One solution is to simply take a random variable x that is greater than or equal to 0. In this case, our sum either converges to a non-negative real number or it goes to plus infinity. This sum is also well defined if it absolutely converges. This means that the sum of absolute values of the summands, namely the sum of x and s, of absolute value x times p of x equals x, is less than infinity. Here we can group terms corresponding to plus x and minus x together to obtain that this is equal to the sum of x in the image of the function absolute value x, so this, of x times the probability that the absolute value of x is equal to x. This expression is just the expectation of absolute value x, which is always defined because absolute value of x is greater than or equal to 0. Therefore, we can also define the expectation of x if E of absolute value x less than infinity. The expectation is not defined if x doesn't satisfy at least one of these properties. Let's see if E indeed satisfies 1 and 2. 1a is greater than or equal to 0. Therefore, we can just plug in 1a into this definition for E of x to get that E of 1a is equal to that sum where we have just one non-zero summand corresponding to x equals 1. So the expectation of 1a is equal to 1 times the probability that 1a equals 1, which is nothing but P of A. For 2, we will need some preparation. Namely, we will show how to evaluate the expectation of g of x. It could happen that this expression is undefined, so we will work under the assumption that it is not. By definition, E of g of x is equal to the sum of y and t of y times P of g of x equals y. We have already seen how to split up this event as a disjoint union in the proof of the fact that g of x is a random variable. Using sigma additivity here, we obtain that this is equal to the sum of y and t, the sum of x and s such that g of x equals y of y times p of x equals x. Since we assume that e of g of x is well defined, either all our summands are non-negative or the sum absolutely converges, so we may just swap these two sums to obtain that this is equal to the sum of x and s, the sum of y and t, such that g of x equals y, y times p of x equals x. This sum here is kind of funny because we have exactly one value for y that we are summing over, namely g of x. So we can just plug this in to obtain that all of this equals to the sum of x and s of g of x times p of x equals x. So we have now proven the transformation formula for the expectation of random variables. Let me note that the work I did previously on the expectation of absolute value x was just a special case of this, with g being equal to the function absolute value. We will use this result because we want to interpret ax plus by as a function of the random variable x, y. Here, x, y refers to a random variable in R squared, which is not a problem here. The transformation formula yields that if the expectation of ax plus by is defined, then it is equal to the sum of x, y in x of omega cross y of omega of ax plus by times p of x, y equals x, y. We can split this sum and use the fact that the sum over all y of p of x, y equals x, y is by sigma additivity equal to the probability that x equals x. Since the same holds when swapping x and y, we get in total that this is equal to the sum over all x of x times p of x equals x, all times a, plus b times that expression for y. We see that these are just the expectations of x and of y if defined, and therefore point 2 also holds if everything is defined. I want to make two notes before finishing the expectation chapter with two inequality. First of all, I want to say that linearity of expectation is incredibly important. You will often see it with scalars being equal to 1, but possibly more than 2 summands as variables. The reason is that linearity of expectation is always applicable regardless of the dependencies of the summands. One typical example of this would be my motivation chapter in the solution of EMO 2023 problem 5 on this channel. Secondly, I want to continue with my example on the right. Namely, I will evaluate the expectation of the random variable x. Since it is clearly defined, we can just plug in the definition to obtain 1/4 times 2 plus 1/4 times 1 plus 1/4 times 1 plus 1/4 times 0, which in total is 1. This also matches our intuition because with two 50-50 coin flips, we expect to see one head. Interestingly, I think our intuition uses linearity of expectation here. Namely, we can interpret x here as the sum of the following two indicator variables. Firstly, the indicator for the first throw being heads, and secondly, the indicator random variable for the second throw being head. Since each coin has a probability 1/2 of landing on heads, the expectation of those indicator variables is 1/2, and therefore their sum equals 1. Since linearity of expectation doesn't require any independence, this also implies that the same result holds if we have two fair coins that are not independent. Now we can easily deduce that the expectation is monotonous in the following sense. If we take any two random variables, x, y, such that x is greater than or equal to y and their expectations are defined, Then we have that the random variable defined by x minus y is greater than or equal to 0. Therefore, by definition of expectation, its expectation must also be greater than or equal to 0. But now we can rewrite this as the expectation of x minus expectation y to finally conclude that the expectation of x is greater than or equal to the expectation of y. This result on the monotony of the expectation now allows us to prove the Markov inequality. This result tells us that for a non-negative random variable, if we know that its expectation is small, then it cannot have a high probability of being larger than some number lambda greater than 0. To prove this result, we simply notice that the random variable x is greater than or equal to lambda times the indicator random variable of x greater than or equal to lambda. Applying monotony of expectation, we obtain that Ex is greater than or equal to the expectation of the right side. We can first use linearity of expectation to get a lambda in front, and then note that the expectation of 1 x greater than or equal to lambda is simply the probability that x is greater than or equal to lambda. Since lambda is positive, we can divide on both sides by lambda to obtain the desired result. As promised, I'm now going to return to the end of chapter 1 to prove the principle of inclusion-exclusion. To evaluate the probability of the union of the AI, we notice that this is just the complement of the intersection of the complements of the AI. This probability is simply the expectation of the corresponding indicator random variable, and we can notice that the indicator variable of the intersection of events is just the product of their indicator variables. Now let me express the indicator random variable of AI complement as 1 minus the indicator of AI. We can multiply this out and use linearity of expectation to conclude that this is equal to the sum of k of minus 1 to the power of k plus 1, because we have this minus sign here, and then of the sum of I1 less than up to ik of the expectation of the product of I going from 1 to k, or j going from 1 to k, of 1 aij. Finally, we can rewrite this product of indicator variables as the indicator variable of the intersection of the corresponding sets. And now this expectation is just the probability of the intersection of j going from 1 to k, aij. And although this was a pretty long one-line proof, I'm happy with it and will finish the video on the probability skill page here. Maybe I will do a second video related to the probability skill page. There's still a lot of content to cover. For example, with respect to variance, we can talk about the Cauchy-Schwarz inequality, whose equality case has a nice interpretation in this context, or the Chebyshev inequality, which is also known under the name of the second moment method in general. I hope you enjoyed the video and maybe learned something, and wish you a nice day.